All right, for section 7.6, we do completely skip 7.5. For section 7.6, we're going to look at modeling data. Specifically, we're going to look at exponential, logarithmic, and quadratic functions. We're going to do a good bit with exponential, a little bit with logarithmic, and then we'll do a good bit with quadratic. Okay? So first up are exponential functions. So let's just kind of dive in. I've tried making this video twice. I get almost to the end, and then I just get all tongue-tied and I've had to start over. So okay. So before we dive into the actual definition of an exponential function, I should probably dive into exponential notation, just as a quick reminder. So when you're dealing with exponential notation, we could have something like 2 to the fourth. Okay, exponential notation is shorthand for repeated multiplication. So if I write 2 to the fourth, that really means take 2, multiply it by itself 4 times. So we would get 16. Now we have two definitions here. One, the exponent, the second, the base. The base is the number being repeatedly multiplied. And then the exponent tells us how many times to multiply the base. All right, so that's just a really quick, super quick reminder of what is exponential notation, because it goes hand in hand with this idea of an exponential function. Okay? So there you have it. Now, as for the definition of an exponential function, it says here the exponential function with base b is defined by y equals b to the x or f of x equals b to the x. Don't get too hung up on the f of x. Remember, when we have something that we know represents a function, it fits the definition for a function, we let y equal f of x. So I could rewrite this. I could write it y equals b to the x or f of x equals b to the x. Same thing, okay? Now we do have a condition b is a positive constant other than 1, and then x is any real numbers. What's different about an exponential function compared to everything we've dealt with so far is that the variable is the exponent. We've had variables and we've had exponents before, but the exponent was some known value and the base was the variable. We're flip-flopping things here, okay? So what I want to do first is just kind of show you how to graph. We'll do it by hand and then we'll verify our work in Desmos, okay? Then we're going to look at two application problems, all right? So first up, it says consider the function y equals 2 to the x power. We want to fill in a table of values that we can then use to graph this. So graphing by point plotting, we did it a little bit in the first part of this chapter, and then we stopped when we started talking about linear stuff because linear functions are kind of nice and easy to work with. So we talked about just graphing lines, we talked about systems of linear equations, we talked about linear inequalities and systems of linear inequalities, and we didn't really use point plotting, okay? When you're dealing with non-linear stuff, exponential is definitely not linear. Table of values, point plotting, that's going to be kind of your go-to method for graphing. Okay, so how do we do this? Well, we take our function and we evaluate it for different values for x. So we have a table of values here with 5 different x values. We're going to take our function, evaluate it one at a time for each of those x values, and figure out what y has to be for each given x. Then we plot those points and connect them with a graph. So we get y equals 2 to the x, but x is negative 2. We get to go back to our exponent rules from 5.6. When you have a negative exponent, it really just means that factor needs to change places in a fraction. So this is really 1 over 2 squared, or 1/4. Or you could write it as a decimal 0.25. That would be fine. Okay? And then you just repeat. It's kind of like a lather, rinse, repeat situation. So we get y equals 2 to the x, but x is going to be negative 1. Well, 2 to the negative first power is really 1 over 2 to the first power, or 1/2. And we could write that as 0.5 if we wanted to. Keep going. We get y equals 2 to the x, but x is 0. You have to go back to your definition of the 0 exponent. If you have a factor with 0 as the exponent, it just makes that factor equal 1. Okay? And then we get y equals 2 to the x, but x is 1. This is just regular exponential notation that we're kind of super familiar with. 2 to the first is just 2. And then we get y equals 2 to the second power, which is 4. Now, here's the thing with exponential functions. Exponential functions have this explosive growth. Okay, so you kind of start out small and then you just go, whoop, you like have this explosive exponential growth. So if you ever hear people talk about exponential growth, it's just this like explosive growth. So things start off small and they shoot upwards. All right, so let's plot these points. We're going to start at the top of our table and go down. So when x is -2, we're saying y has to be 0.25. So at the origin, I go to the left 2 and then up just a quarter. Okay? And then when x is -1, y has to be 0.5. So at the origin, I go to the left 1 and up halfway. And then when x is 0, I go up 1. So at the origin, I don't go left or right. I just go up 1. And then for 1, 2, at the origin, I go to the right 1 and up 2. And then for 2, 4, at the origin, I go to the right 2 and up 4. Okay, so this is what is happening with an exponential function. Okay, notice the growth starts out really small and then it just kind of shoots upwards. Okay, so let's take a peek of this in Desmos. Okay, I may have stuff in Desmos. I may have to reload it. Let's see. Well, that's our calculator. Let's go to Desmos. I think graphing's a little bit easier in Desmos. So instead of typing f of x, you can just type in y. Remember that. So if you get a function that's in function notation, you can just type in y for f of whatever. So we get y equals 2. Now to type in an exponent, you can hold down shift and then type 6 on your keyboard, and that'll raise you to that superscript world. And then we just want to type in an x. Okay. Now let me reload this because I was fiddling around before I made this video. So we're going to reload. We're going to do the same thing. So y equals 2 to the x. And you can see really nicely our graph. Okay, so there you have it. So if we zoom out a little bit, when x was -2, we're at well, 0.25, I'm off a little bit. And then when x was 1, we're at 0.5. When x was 0, we're at 0.1. When x was 1, we're at 2. And then when x was 2, we're at 4. Okay, so you can see really clearly there those points. You can also, if you type your equation in the form y equals, which is exactly what we have, you can go to this little settings like cog wheel thing above where you type in your equation, click that, and then it'll give you options for what you could do with that equation. You just want to hit this first option, which creates a table, and you can see this table exactly matches our work. We have x is -2, y is 0.25, x is -1, y is 0.5, all the way down the list, just like what we did on paper. Okay? Now let's go back to the worksheet. We have two application problems, so just word problems. The first one, I don't think I worded it very well. I was trying to condense it into a certain space, and I think it got a little wacky. But here it says, consider the models f of x equals 0.074x plus 2.294. That is a linear model. Remember, we can replace f of x with y, so this is really just y equals 0.074x plus 2.294. And then we have g of x equals 2.577 times 1.017 to the x. So we could write that as y equals 2.577 times 1.017 to the x. Okay. Y equals the 0.074. That is a linear function. Okay. We have two variables, y and x. They are both to the first power. And then the second one, the g of x function, it is exponential because your exponent is a variable. And basically what I didn't put very clearly here is these both model the world population, okay? But we are specifically modeling the world population where X is the number of years after 1950. So in 1951, X would be 1. In 1955, X would be 5. In 1960, X would be 10, and so forth. Okay, so we have these two different models that are modeling the same thing, and what we want to know is which model best estimates the world population at a given time. So for part A, it says the world population in 1970 was 3.7 billion. Okay. All right. It says which function serves as a it's late, y'all. A better model for this particular year. So is the linear function or the exponential function going to be our better bet? So let's say we have f of, well, what in the world is x? Well, we're interested in 1970. And remember, x is the number of years after 1950. So we're going to let x equal 20. So f of 20 equals 0.074 times 20 plus 2.294. And then for the exponential model, we would get g of 20 equals 2.577 times 1.017 to the 20th power. Now, which one is better? Okay, you can do this two ways. You can go to Desmos or to the graphing calculator. Let's go to the graphing calculator first. Okay, so the linear model, you don't have to type in the y equals, just type in the stuff after the equals. So we have 0.074 times 20, don't put a decimal, put 0, plus 2.294. Okay, so we get 3.77. Now remember, it said in 1970, the population was 3.7, so we want to subtract 3.7, and we can see that this model overestimates the population by 0.074. Okay, now let's do the exponential one. So we had 2.577 times 1.017, 017. There we go. Raised, in this case, to the 20th power. So to get to the caret button here, look at the division button on your calculator. Directly above that is the caret. That'll put you in that superscript world. And then type in 20. All right, so we get 3.61. So this underestimates the actual population. So we would take 3.7 and subtract 3. Let's just go 3.61 here. So it underestimates the population by 0.09. So in this case, which of these two models was closer to the actual population of 3.7? Well, in this case, the linear model was a little tiny bit of a better estimate. It was off by 0.074, whereas the exponential model was off by 0.09. So let's go back to our worksheet. Okay. We had here 3.774. We had here 3.61. This overestimated by 0.074. This one underestimated by approximately 0.09. So the question says, hey, which one's better? Well, this is going to be the better model. Oh, don't do that. I cannot believe I just did that. This is the better model. Okay, so linear is the better estimate. In 1970. Okay, now for part B, it says the world population in 2010 was 7 billion. Okay, which function serves as a God bless, I can't say better to save my life. Which function serves as a better model for this year? Well, in 2010, that would be 60 years since 1950, so we would let x equal 60. So we would get f of 60 equals 0.074 times 60 plus 2.294. And then we would get g of 60 equals 2.577 times 1.017 to the 60th power. Okay, so let's go back to the calculator. All right, now here's a trick. You can do a couple things. You can get your calculator to store in different values for x. You can just type them in as is. These two functions, they're not that terrible. So, I mean, if you had to retype it, like, who cares? It's not that big a deal. But if you don't want to retype it, you can just scroll up until whatever function is highlighted, hit enter, and it'll bring it back down. And then all we have to do is type over the 20 and make it a 60. And so we can see in 2010, the linear model estimated the population at 2.734. Now remember, the actual population was 7, so this is definitely an underestimate. So we want to take 7 minus 6.734. And so we would say this one underestimates by 0.266. And then let's do the same thing, but we're going to do the exponential model. I am struggling to speak tonight, y'all, and I swear to God, I had nothing but Diet Coke with my dinner. All right, so we're going to take the exponential model. We want to replace the 20 with a 60 and hit enter. And so in 2010, the exponential model was let's go 7.09. Well, let's do 7.086, okay? So then if we did 7.086 minus the actual population of 7, hopefully you don't have to actually do this on your calculator, but all the same, we get that this one is an overestimate by 0.86 or 0.086. So over by 0.86. All right, let me make sure I have that written down before I go to the worksheet. And if we go to the worksheet, we get the right pen, first of all. We get that the linear model said that this was 6.734, which was under by approximately 0.266. And then the exponential model, we got 7.086, which was over by 0.086. So which model is better? Which one is closer to the actual population of 7% or 7 billion? This one is, okay? So in 2010, the exponential model is better in 2010. Okay. Now you could also do all of this in Desmos at kind of like all at once. So let's go to Desmos. Okay. So we want to go to Desmos, clear out the old junk. All right. We want to type in the linear function, which was y equals 0.074x plus 2.294. Okay. Whoops. I did one too many. 294. Okay, now remember, if you choose this little settings cog up above where you type your equation, it'll allow you to get a table of values. Now, we don't want all of this. We just are interested when x is 20 and when x is 60. So you can go down to the bottom and then just backspace. And then for -2, type in 20. For 1, type in 60. And it does all the work for you. Okay? Now, for the exponential model, we have y equals 2.577. And then in parentheses, 1.017, end your parentheses. And then remember, hold down shift and type 6. That'll take you to the exponent world, and you type in an x. And then you can go back to that settings cog. It'll give you the option for a table. Remember, we don't need those other values. We're just interested when x was 20 and when x was 60. And there you have it. You can see really quickly a bit of an image of these graphs. Now, if you wanted to, you could change your x-axis here. So in Desmos, when you are in the graph screen, there's this little wrench in the upper right-hand corner. If you type that, it'll allow you to tweak your X and your Y axis. So we're talking Y as population. We could start it at 0, and then let's say we go to like 10, and we could just increment by 1, okay? Now for the Y axis, we're talking years since 1950. So let's just say, I don't know, we could do negatives here, but let's just go 0. And then let's say we go 100, but let's increment by 10, okay? And then if we go back, you can see very clearly what's going on here. So you can see here around a little after 1950, and then here again in 2000, the two models would be about the same, but then you can see where one shifts and is better or worse than the other. Okay, so there you have it. If we wanted to compare this to like when a population was a certain thing, so we could say, hey, at a certain point, we knew that the population was 7 billion. We could type y equals 7, and it'll type in a vertical line so that you can compare, hey, the blue model or the black model is closer at this particular x, at this particular year, so some particular x value. Okay, so you can play around with Desmos quite a lot and get a lot of information about your graph. Okay. Now I am going to refresh this because we're going to do another example. So let's go back to the worksheet. And this is the one where I keep getting so tongue-tied. I've had to redo this video. This is the third time I get to this point and then I just get all like blah and I can't speak. So we're going to try really hard. Okay, first of all, we have a definition. So we already know that in math, there's this irrational number called pi, which is 3.14 blah, 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 blah. Okay, we just use the pi symbol to represent this number, which has a real world meaning. It's really the ratio of the circumference of a circle to the diameter of the circle, but don't worry about that. Just know it's an irrational number. We always use the symbol pi to represent that. Well, there's another irrational number that has a lot of applications in exponential functions, and it is e. Okay, the irrational number is approximately 2.72. So if we use e in math, 2.72. Okay, now with that said, you will see e again. It'll show up when we talk about finance. Okay, so don't forget about e. Now, here's the deal. Example 3 here says medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. This is modeled by the exponential function r of x. So think r is the risk And X, I didn't mention explicitly what X was, but X is the blood alcohol concentration. Okay. So R of X equals 6 times E raised to the 12.77 times X power. Okay. So it says here for many states, it is illegal for drivers under 21 years of age to drive with a blood alcohol concentration of 0.01 or greater. What is the risk of a car accident with a blood alcohol concentration of 0.01, round to one decimal? Well, what we want to do is take this function R of X and we want to replace X with 0.01 to calculate the increase of our risk, okay? So we get 6 times e to the 12.77 times x, which is 0.01. And we can just do this really easily on the calculator. So let's go to the calculator. All right. So we had, what was it? Let me flip my page. What was it again? 6 times E. Now, E, you can do it two different ways on the graphing calculator. So if you look at your division button on the graphing calculator, in the upper left corner, it has an E, which means if you hit the blue second button and then hit division, it'll type in an E. However, if you go down to your on button, which is the bottom of the first column, and then go up to, there is a button that has an LN on it, and in the upper left-hand corner of that button, it has e to the x. So what it'll do is it'll type in e, but it'll automatically set you up to type in some exponent. So to get to that button, we hit second LN. So that's what I'm going to do. So second, and then type in that LN button, and it types in your e, and then it automatically bumps you up to that superscript where you can type in your exponent, which was 12.77 times 0.01 and then hit enter. And we get that the increase or the risk increase is going to be 6 point, I think it said one decimal place, so 6.8. So let's see here. So it says for many states it's illegal, blah, blah, blah. What is the risk of a car accident with a blood alcohol concentration of 0.01, round to one decimal place? 6.8. So let's say there's a 6.8% possibility of accident with a blood alcohol of 0.01. Okay, now part B says, excuse me, part B says, what is the risk of car accident with a blood alcohol of 0.08? So it's the same thing, but we want to replace X with 0.08. 6 times e to the 12.77 times 0.08. Excuse me. So let's go to the calculator. And we can do that thing where we just jump up and grab the old function. All I need to do is type over to 0.01 and make it a 0.08. And then hit enter. And so if we go one decimal place, we get 16.7. So go back to the calculator. And we can see here that with a blood alcohol of 0.08, the risk is 16.7. So let's say there's a 16.7% chance of accident if your blood alcohol, or increase in accident if your blood alcohol is 0.08. Now, Desmos. Desmos will do all of this too. So if you wanted to, you could go to Desmos. Now we're going to have to do some playing around with Desmos, okay? So we had y equals 6. Now to type in E, just use the button on your calculator. So 6E, and then shift 6, 12.77x. Okay, so you can see our graph here, but it's really hard to tell what's going on. Okay, and the reason for that is our settings. So let's go to this little wrenchy thing in the upper right-hand corner. Now for X, X is the blood alcohol. It can't be less than 0, so we're going to start with 0. And then we're going to go to just 1, okay? But we can increment by, let's not even go to 1. Let's go to like 0.25, and we can increment by 0.05. Okay, and then the risk, you can't have less than 0% risk. Let's go 0 to, I don't know, 50, and we'll increment by 10. Okay, you can change the window in Desmos really easily. So again, you go to this little wrench, and then your x-axis, you tell it where you want it to start, where you want it to end, and then the step tells you how you increment your x-axis. And then for the y-axis, again, where you want it to start, where you want it to end, and how you want it to increment. Okay, so let's see what we have here. So you can see here that when we have a blood alcohol of 0.5 or 0.05%, our risk of accident is about 11.3, okay? And if we have a blood alcohol of 0.1, our risk of accident is, well, it's kind of hard to see here, but it's a little bit less than 7, okay? I'm just not clicking on it quite right. Let's see if I can get 0.01. Well, anyway, you can see that if I were able to click on it exactly, we could get that 6.8%, okay? When you have a blood alcohol of 0.1, your risk of accident is way up here at 21.6%, okay? Now, you could do the exact same thing that we did in the previous example with world population. You could click this little settings cog where you type in your equation and choose table. We don't want all these crazy values to get rid of them. What we're interested in is when the blood alcohol was 0.01 and when the blood alcohol was 0.08, and you get the work right there. Okay, so you can see here when we were at 0.01, we have our blood alcohol of 6.8%, or not the blood alcohol, the risk is 6.8%. And then here, when the blood alcohol was 0.08, the risk was 6.7%. Okay, so Desmos is amazing when you're dealing with the table of values. I'm okay with Desmos doing the table of values, but you still have to show me some stuff on paper typically. Okay, so there you have it. That is, praise the Lord, finally got through this video. That is exponential functions. Okay, so let's go back to the worksheet. Make sure we finished up. I think we're good here. So we have finished our exponential. Make sure you know how to just graph one by hand. You can also use Desmos to create the table of values, but you need to be able to plot those points by hand. And make sure you understand how to play around with these word problems. In this case, we were looking at whether a linear model or an exponential model did a better job estimating the world population. And then we had this exponential model, which represented the risk of accident with particular blood alcohol level. Desmos is a really cool tool for stuff like this because it can do some of that plugging in for you. It can create those tables of values really nicely.